Everybody, I just wanted to talk a little bit about the other things we did in Math 115 last week that I hadn't made a video for. Um, so if you remember in the previous video from last Monday, we started out talking about circles, and we had things like there was a boat or something, and we wanted all the points that were maybe 2 miles away from that. So 2 miles was our radius of this circle. So if you want to find all the points that are a certain distance from a fixed point, it's going to end up being a circle. Imagine that you're here and you have a friend here who's holding a string that long. Okay, maybe not 2 miles, but a shorter distance. And you hold that string tight and they're going to walk. They can't just keep walking in a straight line. The string's going to stop them. But if they keep walking, it's going to be all the way around in a circle. We also talked about when two circles come together, there's 3 options. They can either be far enough apart that they don't intersect, they can be a certain distance apart where they intersect in one location, or they can intersect in 2 locations. And this was the example of our treasure chest, our treasure map, and it said if it was a certain distance from point A and from point B, different distance from point B, where could it be? We said, well, with those, you could have 2 different locations. We'd either need a third piece of information or you'd have to look in both locations. So in class the other day, we also talked about the same idea, but with spheres or balls. So it's a little bit harder to draw. I certainly can't draw it very well. But if you picture like 2 soap bubbles, let's say, big, you're blowing bubbles, and they come together, okay? Those spheres, if they kind of intersect now, they're not just intersecting on a plane, they're intersecting in space. So, first of all, let's think about what a sphere is. If a circle is all the collection of points in the plane that's a certain distance from the center, a sphere is the same idea, except it's all the points in space. So now, if I want to find, this is my distance. So if I want to find all the points in a plane that are this distance from me, I could have my little marker here, and if I turn around, that's going to give me a circle. But if I want to think about in space, then not only am I going out in this way, but I'm going up and down and at a diagonal and down at a diagonal. So you can picture I'm kind of inside this bubble that I'm creating all this distance away from me. So that's my sphere. So when 2 spheres come together, they don't just touch at individual points. If you can kind of picture that 2 soap bubbles sort of colliding, a whole slice of that would be where they collide, right? So what happens is when 2 spheres come together, their intersection point is actually going to be a circle. If you took this orange and you kind of slid off the edge and the edge of another orange and put them together, right, that's where they're intersecting. So that's going to be a circle. So just a little bit, it takes it 1 extra dimension. It goes from 2-dimensional to 3-dimensional. Then if I had a third orange in there and kind of was able to intersect that also, then with 3, then I'm down to kind of 2 points, or a little slice like this. And we talked about how this is how GPS works, okay? So there are a series of satellites in space, and there are 24 of them in different orbits, or at least 24 of them. So at any point where you are on Earth, at least 4 of those satellites can see you. So one satellite knows, okay, you're 150 miles away from me. It knows that, but it doesn't really, you could be anywhere still 150 miles from that satellite. But then another satellite says, oh, you're, 118 miles away from me. So now between those 2, there's a smaller group. I can't be over here because that's too far from that other satellite. So there's a smaller area, a circle of where I could be. And then a third satellite says, oh, you're this far from me. Now it's narrowed it down more. With 3, you'll have it narrowed down to 2 places. That 4th one will narrow it down to 1 place, or sometimes you don't even need that because maybe one of those 2 places is on Earth and the other one's up in space. So we can kind of assume you're down on Earth. So that's just an idea of how GPS works, or also another sort of a real-world example of where, the sphere intersections would be. It's called triangulation, even if you have these here also. So let's say you are 3 boats in the water and you get some kind of like SOS beacon and you know how far away it is, but you're not sure which direction. 3 boats together could pinpoint where that SOS is coming from. Okay, so that was one thing we talked about. The other thing we talked about was I had asked you in the what am I going to say? To-do list to take a round object of some kind, and measure the circumference and the diameter. So the circumference is a little bit tricky, right? And I asked you to be as precise as you possibly could. So I took a little piece of paper here, and my paper wasn't quite long enough, but I wrapped it around. I probably should have just got a longer piece of paper, but I wrapped it around as far as I could, made a little line, and then wrapped it again so I could figure out how much more, and then I held it up to my ruler. So I didn't remember to write down how much this was. So let's see. So, and I am going to measure in centimeters. So I put my paper on my ruler here at the 0 mark. Remember, we don't go to the edge of the ruler. And when I measure this is 21.7, and then I have to add this other little part here. So let me write this up here so I remember. 21.7 centimeters plus my other part that got me the rest of the way around my circle is 4.5. Okay, so all together my circumference is 26.2 centimeters. Okay, and then the other thing that we wanted to measure was the diameter. So again, you're doing this with anything that you have at home. It could be the top of a soda can. It could be the top of a can of green beans. It could be anything that you have that's circular. Okay, so I just did this part right here. You can see that this lip is a little bit bigger. So I did this part right here. So I'm going to do my diameter across that part. And we said sometimes if you have a can or something, there'll be like a little dimple in the middle, so you know right where the middle is. But otherwise, we just kind of have to guess where that middle is, that widest part. Make sure, again, that you're right in the 0 line, not on the edge. And this is going to be 8.2. Let's see, do I want to go 8.2 or 8.3? I'm going to say 8.2 centimeters. Oh, lost my ruler. Okay, so that's my diameter, is 8.2 centimeters. Okay, now, I asked you to do those two things and then divide circumference divided by diameter. Okay, and again, I don't care if you use centimeters or inches. Centimeters are a little easier in some ways. We talked about that, right? Since it's divided into 10, we can just put point whatever because it's tenths. In inches, you'd need to use fractions. All right, so now I'm going to divide my circumference divided by my diameter, and I get 3.195. Bunch of other numbers there too. Okay, so if you did not already do this, I would ask that you stop the video and try find some circular object, measure around the circumference, measure across the diameter as best you can. Okay, and then come back to the video. Okay, so you can go ahead and pause it, find something to do that with, and then come back. Okay, so hopefully you did that and you divided those two. Now, this is one of those situations where I used to try doing a lesson when I taught this for Math 90. I used to try doing a lesson where I handed out all kinds of different lids and whatever, yogurt containers, whatever it was, in my class, and I wanted everyone to measure the circumference and measure the diameter and then divide them. Okay, and the idea was that once we got all of our numbers here, we'd be able to see a pattern. But unfortunately, sometimes, the measurement isn't as precise as you want. So I'd do this and I'd end up with stuff all over the place in terms of numbers, and it didn't really do what I wanted it to show. So this is one of those lessons that I've had to, you'll find this too, where you kind of have to pivot and change things either midstream or, make a note for next time that you go to teach that didn't quite work. So what I've done sometimes then is either I measure a bunch of things, or if people work together, sometimes they're a little bit more careful because they kind of catch each other. But if you were pretty precise with your measurements, you should have something that's 3 point something or other. Okay, mine is a little bit high here, so something here was a little bit off. But you hopefully, and if we had more people, we could kind of compare our answers, but you should notice that when we take circumference divided by diameter, we should get answers that are roughly around 3.14, which you may remember as pi. Okay, that's the approximation of pi. And so you might just remember, well, pi is this thing that we use with circles, right? If we have the circumference of a circle is pi times the diameter, or 2 pi times the radius. These two mean the same thing because 2 times the radius is the diameter. The area of the circle is pi r squared. There's going to be a pi anytime we have a formula for volume or surface area that has to do with something with a circle, like a cylinder or a cone. It's going to be included in there. So, but if we look at what this is saying, when we do circumference divided by diameter, and if you think about doing a little algebra with this equation, you can see why, we always get pi. Always, always, always. Okay? Does not matter if I use this little tiny circle here, if I use my lid, if I use some, if you go to a park and there's a big circular, concrete piece, you do that. Whenever there's a circle, the circumference divided by the diameter is always going to equal pi. Another way of thinking about that is that the circumference always has to be a little more than 3 times as long as the diameter. So if I took my diameter and then was able to spread it out along in here, it's going to take 3 of those and a little bit more. It kind of makes sense if you think about it. There has to be some kind of relationship that's always there. Because if this is my diameter and my circumference is going to be more than this, then it's going to have to maybe be a little bit oval or something to kind of fit in that extra length. And if I have a certain diameter and my circumference is not big enough, so let's say if I put it on, it would only go to here, well, that can't be. So to close it down, I'd have to, again, do something kind of oval in this way. So in order for it to stay circular, it has to have this relationship where the circumference divided by the diameter is always a fixed amount. And that fixed amount happens to be pi. Okay, so the last thing then we did is we talked about a cylinder. So I have sort of a cylinder here. I have a bubbly water soda can. So this is not exactly a cylinder, right? Because it goes in here at the top and the bottom, but pretend it was all the way up. So the volume, first of all, of that, the volume of any solid shape is going to be represented by capital B times H, where capital B is the area of the base. And then we can sort of make it more specific to the specific shape by thinking about what shape that area, that base is, and how I'd find the area. Okay, so I'm getting kind of close to the maximum of what I can upload to YouTube, so I'm going to stop this video and I'll start another one and we'll finish it up. But think for a minute about, for a cylinder, what shape the base is. So what would that area of the base formula be? We'll start with that in just a second.